Hi friends, let's move ahead and understand about the three OOPS principle in Java. So your all object-oriented programming languages provide mechanisms that help you implement the object-oriented model. They are encapsulation, inheritance, and polymorphism. So let's quickly take a look at all of these, starting with encapsulation. Your encapsulation is the mechanism that binds together code and the data it manipulates, and definitely keeps both safe from outside interference and misuse. One way to think about encapsulation is as a protective wrapper that prevents the code and data from being arbitrarily accessed by other code defined outside the wrapper. Your access to the code and data inside the wrapper is tightly controlled through a well-defined interface. To relate this to the real world, consider that you have an automatic transmission on an automobile. Here it encapsulates hundreds of bits of information about your engine, such as how much you are accelerating, the pitch of the surface you are on, and the position of the shift lever. You as the user have only one method of affecting this complex encapsulation, is by moving the gear shift lever. You can't affect the transmission by using the turn signal or windshield wipers. Thus, the gear shift lever is a well-defined interface to the transmission. Furthermore, what occurs inside the transmission does not affect objects outside the transmission. Say for example, shifting gears does not turn on the headlights. Because an automatic transmission is encapsulated, dozens of car manufacturers can implement one in any way they please. However, from the driver's point of view, they all work the same. The same idea can be applied to the programming skills. The power of encapsulated code is that everyone knows how to access it and thus can use it regardless of the implementation details and without fear of unexpected side effects. In Java, the basics of encapsulation is the class. Here a class defines the structure and behavior that will be shared by a set of objects, and each object of a given class contains the structure and behavior defined by the class, as if it was stamped out by a mold in the shape of the class. For this reason, objects are sometimes referred to as instance of a class. Thus, a class is a logical construct, an object has physical reality. So, when you create a class, you will specify the code and data that constitute that class. Collectively, these elements are called members of the class. Especially the data defined by the class are referred to as member variables or instance variables. So here the code that operates on that data is referred to as member methods or just methods. In properly written Java programs, the methods define how the member variables can be used. This means that the behavior and interface of a class are defined by the methods that operate on its instance data. Since the purpose of a class is to encapsulate complexity, there are mechanisms for hiding the complexity of the implementation inside the class as well. Here each method or variable in a class may be marked private or public. The public interface of a class represents everything that external users of the class need to know or may have known. And the private methods and data can only be accessed by code that is a member of the class. Therefore, any code that is not a member of the class cannot access a private method or variable. To understand more about your encapsulation, so here you can see the public methods can be used to protect private data. As you can see, your circle represents public instance variables, which is over here outside of the circle. Just assume this is your class A. Like I've mentioned that public instance variables is something that you see over here in circles. Next comes your public methods, which is on the outer circle in the form of a triangle. Then you have private methods and private instance variables, which are inside your public methods in the form of filled triangles and filled circles. So this is an example of your encapsulation where public methods can be used to protect your private data in the form of your methods and instance variables. Moving on next, let's talk something more about inheritance. Your inheritance is the process by which one object acquires the properties of another object. This is important because it supports the concept of hierarchical classification. For example, say a golden retriever is part of classification dog. So for that, let's look at a couple of images. So say for example, like I had said, golden retriever is part of the classification dog, which in turn is part of your mammal class, which is under the larger class animal. Without the use of hierarchies, each object would need to define all of its characteristics explicitly. So as you can see, Labrador and Golden are two types of your retriever. Then your Domesticus has two types again, Retriever and Poodle, which in turn is a part of your Canin. Canin is part of your mammal, and mammal is in turn part of your animal. So your each and every object will inherit characteristics of the other or of the superclass. However, by use of inheritance, an object need only define those qualities that make it unique within its class. So here it can inherit its general attributes from its parent. So here the parent class is animal, and mammal will inherit few of the characteristics of the animal. Similarly, the same thing applies for reptiles, which inherits some of the features or the characteristics of animal. Thus, it is the inheritance mechanism that make it possible for one object to be a specific instance of a more general case. Here, most people naturally view the world as made up of objects that are related to each other in a hierarchical way, such as your animals, mammals, and dogs. But if you wanted to describe animals in an abstract way, you would say that they have some attributes such as size, intelligence, and type of skeletal system. Your each and every animal or each and every uh, animal type that you see will have its unique characteristics. So your even animals also have certain behavioral aspects such as they eat, breathe, and sleep, which everyone might have common. So this description of attributes and behavior is the class definition for animals. So if you wanted to describe a more specific class of animals such as mammals, they would have more specific attributes such as type of teeth and mammary glands. This is known as a subclass of animals, where animals are referred to as mammals, a superclass. As you can see here, your animal is the superclass of mammal and reptiles. Since mammals are simply more precisely specified animals, they inherit all of the attributes from animals, and a deeply inherited subclass inherits all of the attributes from each of its ancestors in the class hierarchy. So your inheritance interacts with encapsulation as well. If a given class encapsulates some attributes, then any subclass will have the same attributes, plus then it acts as part of specialization, as you can see in this diagram. This is a key concept that lets object-oriented programming grow in complexity linearly rather than geometrically. So a new subclass inherits all of its attributes of all of its ancestors, and it does not have unpredictable interactions with the majority of the rest of the code of the system. So moving on, next we have is polymorphism. Your polymorphism from Greek means many forms. It's a feature that allows one interface to be used for a general class of actions. Here the specific action is determined by the exact nature of the situation. So consider a stack which is in a last in first out list. Here you might have a program that requires three types of stacks. One stack probably is used for your integers, one for floating, and one for character. The algorithm then that implements each stack is the same, even though the data being stored differs. In a non-object oriented language, you would be required to create three different sets of stack routines with each set using different names. However, because of polymorphism, in Java you can specify a general set of stack routines that all share the same names. More generally, the concept of polymorphism is often expressed by the phrase one interface, multiple methods. This means that it is possible to design a generic interface to a group of related activities, and this helps reduce complexity by allowing the same interface to be used to specify a general class of action. It is the compiler's job to select the specific action as it applies to each situation. You, as a programmer, do not need to make this selection manually. You need only remember and utilize the general interface. So, extending the dog analogy, a dog's sense of smell is polymorphic. If the dog smells a cat, it will bark and run after it. If the dog smells its food, it will salivate and run to its bowl. The same sense of smell is at work in both situations. The difference is what is being smelled, that is, the type of data being operated upon by the dog's nose. This same general concept can be implemented in Java as it applies to methods within a Java program. Here you can see in a diagram. So this is again an example of your OOP principle, where you have animal with different attributes like your age, weight, sex, mammal with different attributes of size and period. Then again, for different animal type, we have different attributes like your tall, length, hunting skills, and so on. So this is a perfect example of OOP principles. So moving on next, a very important feature that we need to understand is that polymorphism, encapsulation, and inheritance, they work together hand in hand. So when properly applied, polymorphism, encapsulation, and inheritance combine to produce a programming environment that supports the development of far more robust and scalable programs that does the process-oriented model. So a well-designed hierarchy of class is the basis for reusing the code in which you have invested time and effort developing and testing. So encapsulation allows you to migrate your implementations over time without breaking the code that depends on the public interface of your classes. And polymorphisms allows you to create clean, sensible, readable, and resilient code. One of the two real-world examples is the automobile. More complexity illustrates the power of object-oriented design. And dogs are of course fun to think about from an inheritance standpoint. But cars are more like programs. All drivers rely on inheritance to drive different types, subclass of vehicles. Whether the vehicle is a school bus, a Mercedes sedan, a Porsche, or the family minivan. Drivers can all more or less find and operate the steering wheel, the brakes, and the accelerator. After a bit of gear grinding, most people can even manage the difference between a stick shift and an automatic because they fundamentally understand their common superclass and the transmissions between them. So here people interface with encapsulated features on cars all the time. The brake and gas pedals hide an incredible array of complexity with an interface so simple you can operate them with your feet. The implementation of the engine, the style of brakes, and the size of tires have no effect on how you interface with the class definition of the pedals. The final attribute, which is the polymorphism, is clearly reflected in the ability of car manufacturers to offer a wide array of options on basically the same vehicle. So for example, you can get an anti-lock braking system or traditional brakes, power, or rack and pinion steering, and in that case 4, 6, or 8 cylinder engines. Either way, you still press the brake pedal to stop, turn the steering wheel to change direction, and press the accelerator when you want to move. The same interface can be used to control a number of different implementations. So as you can see, it is through the application of encapsulation, inheritance, and polymorphism that the individual parts are transformed into the object known as a car. The same is also true of computer programs. By the application of object-oriented principles, the various parts of a complex program can be brought together to form a cohesive, robust, and maintainable whole. As mentioned earlier, every Java program is object-oriented. Or to put more precisely, every Java program involves encapsulation, inheritance, and polymorphism. So, as you can see, many of the features supplied by Java are part of its built-in class libraries, which do make extensive use of encapsulation, inheritance, and polymorphism. So this was all about your OOP principles in Java.